Imagine needing medical care, but the nearest facility is hours away, or simply inaccessible. For millions of people, access to reliable healthcare is limited by distance, mobility challenges, or lack of nearby facilities. Across the United States, large portions of the population live in medically underserved areas. But even when care is available, increasing patient loads and administrative demands limit the time doctors are able to spend with their patients. As a result, important behavioral and physiological cues are often missed, leading to incomplete assessments and delayed diagnoses. We've developed a portable, AI-powered clinical examination system, the Dr. AI Smart Patient Exam Room. Dr. AI can be used to rapidly deploy a functional clinical examination room in virtually any environment. By combining multimodal sensing with automated analysis, the system captures and structures critical patient data, enhancing both access and quality of care. Hi, I'm Sean. I'm an electrical engineer and I'm the team lead.
Hi, I'm Lily. I'm the biomedical engineering student and I'm the procurement lead.
Hello, I'm Carson and I'm a software engineer.
Hi, I'm Danny and I'm a biomedical engineer.
Hi, I'm Victoria. I'm a software engineer.
Hi, my name is Avish Bhatnagar and I'm an electrical and computer engineering major. The objective of the Dr. AI project is to develop a multimodal data collection and analysis platform that captures clinically relevant information during a patient encounter. It integrates audio, facial, and motion sensing in order to capture data such as speech patterns, the emotions of the patient, and gait metrics. These inputs are then transformed into quantifiable data that can be analyzed after the visit, and it enables proper diagnostics. The outputs are also compiled into a standardized after-visit report to support longitudinal tracking across multiple visits.
The goal of the facial analysis system is to monitor the affective state of the patient during the doctor visit. The setup for the system includes a high-resolution web camera, a tripod for portability, and a ring light to capture stable, consistent input of the patient's face. The facial analysis is performed by a custom ResNet convolutional neural network, or a CNN. This model is fed pre-processed video frames and classifies the patient's emotion as being either happy, sad, neutral, angry, or surprised. The system automatically records the dominant emotion detected 2 times per second. This data is then stored to a local database containing the patient's record. This allows us to visualize the distribution of the patient's emotions during the doctor's visit, or across multiple visits to assess changes over time. To ensure reliable performance, we defined 3 key system requirements for the facial analysis system. First, the emotion classifier must achieve at least 75% accuracy. Second, it must operate with a latency of no more than 200 milliseconds per recorded frame. And finally, all collected data must be processed and available for visualization within 2 seconds of the end of processing. The accuracy of the emotion classifier is established in the training process. A subset of the dataset used for training is set aside and passed through the model after training to determine its performance. Our best model achieved a 74.44% accuracy. While slightly below our system requirement, this result represents a trade-off between classification granularity and dataset limitations, and we determined that the performance is sufficient for capturing meaningful clinical trends. To measure inference latency, we recorded timestamps before and after processing each frame using a simple timing function. Averaged across 30 trials, the model achieved a latency of 95 milliseconds per frame, well below our 200 millisecond requirement. Using the same method to measure the latency of the data collection and figure generation, our results showed a latency of around 120 milliseconds, meeting our requirement of 2 seconds.
The audio analysis subsystem focuses on capturing and transcribing conversations between the patient and doctor while also identifying key diagnostic terms and estimating sentiment from speech. By analyzing patient speech, we can monitor how their condition evolves across visits, gain insight into their emotional state, and track their usage of diagnostic terms. We use 2 different microphones positioned near both the patient and the doctor. These inputs are routed through an audio interface, which allows us to process both audio streams simultaneously within our system. Once captured, this audio is then segmented using silence detection to identify when a speaker is finished talking. Each segment is then normalized and passed into faster whisper. The transcription is then analyzed and displayed both the sentiment, keywords, and potential AI diagnosis. To make sure the audio subsystem was accurately capturing speech, the transcription was required to have an accuracy greater than or equal to 90%. Using a custom test, the team compared the transcriptions to what was actually said in these audio samples. The transcription had an overall accuracy of 95.67%. The audio subsystem was also required to have speech segments transcribed in under 60 seconds, so that there was no major delay in transcription time. After extensive testing, the team was able to verify and ensure the transcription passed this requirement. In order to achieve better understanding of the context of the speech in the audio system, it was also required to reach a sentiment and semantic accuracy of 80%. After testing, the team was able to pass this requirement with an accuracy of 85%.
The goal of the gait analysis subsystem is to capture patient movement during functional tasks and quantify clinically relevant motion features, such as walking speed, symmetry, stability, and sit-to-stand performance. Movement can reveal a lot about a patient's condition. Changes in gait, balance, or transitional movements like standing up from a chair may indicate weakness, pain, instability, or neurological impairments. To capture this information, we use an Intel RealSense depth camera, which is mounted on a tripod. This setup gives us both color and depth data, allowing the system to estimate body position in 3 dimensions rather than relying on a standard video alone. During recording, the patient is tracked in real time using media pipe pose, which identifies major body landmarks such as the shoulder, hips, knees, and ankles. These landmarks are then combined with depth measurements from the RealSense camera to reconstruct key positions in 3D space. For walking trials, this includes forward speed, cadence, knee motion, left-right symmetry, and measures of postural stability. For sit-to-stand trials, the system tracks the vertical relationship between the pelvis and upper body to detect transition and estimate how long it takes the patient to rise.
All collected data is synchronized and structured, and enabling consistent and reliable interpretation across multiple modalities. The system also stores this data for post-visit review, allowing clinicians to track changes in patient conditions over time. Because the system is portable as well, it can be deployed in a variety of environments, expanding access to clinical-grade evaluation tools. Overall, Dr. AI improves both access to care and the depth of clinical insight available during patient visits. This demonstrates the potential for AI-assisted systems to support clinicians in delivering more informed and accessible healthcare.